Hello friends, welcome back to this particular subject, Kinematics of Machines. So we were learning about velocity and acceleration analysis method, that too graphical method. We already learned about relative velocity method. Now we are going to begin with instantaneous center method, wherein we already have had a brief introduction about what is meant by instantaneous center, what are the types of instantaneous center, and how to identify an instantaneous center in a given mechanism, and uh, how it will be useful in calculating angular velocity of any link involved in a mechanism. So let us just recap the same thing once again, and then we'll proceed with the instantaneous center. So instantaneous center means the motion of any rigid body along any path can be assumed to be pure rotation. So if you consider any rigid body, let it be moving along any path. For a given particular instant, we can consider it as pure rotational motion, and the center of that particular pure rotational motion is called as instantaneous center of that particular rigid body. The different types of instantaneous center are fixed and permanent instantaneous center, and the last one is neither fixed nor a permanent instantaneous center. Fixed instantaneous center means in this four-bar mechanism, consider instantaneous center I1 and I12 and I14. So these are nothing but the hinges which are connecting link 2 and 1 and link 4 and 1 respectively. So the hinges itself are the instantaneous center. As the link 1 is fixed, these I12 and I14 neither they will never move from their position irrespective of whatever the configuration this mechanism is having. So always they will be here only. So that's what is meant by fixed instantaneous center. Permanent means again consider I23 and I34. So these are the hinges between link 2 and 3 and 3 and 4 respectively. But these hinges are free to move, uh, so that's why they are called as permanent instantaneous center. Neither fixed nor permanent instantaneous center means consider I24 and I13. These are not actually hinges and some arbitrary uh, points. So these locations basically depend on the configuration of this mechanism. So that's why they are called as neither fixed nor permanent types of instantaneous center. The total number of instantaneous center in a mechanism is given by n into n minus 1 upon 2, where n is number of links. For example, for this 4-bar mechanism, we can consider that there are total 4 number of links. So 4 into 3 divided by 2 gives you 6, and those 6 instantaneous centers have been shown here. Now, how to locate the instantaneous centers, that also we discussed. If two links are connected by a rotating pair, that hinge itself will be an instantaneous center. For rolling pair, the point of contact between surface and the roller is instantaneous center. For sliding pair, the instantaneous center will be at an infinite distance on a line perpendicular to line of action of the slider. And if the slider is moving along a curved surface, the center of that curve, let it be internal curve or like external surface, so the center of that curve will be instantaneous center. And then we learned about the angular velocity ratios in terms of instantaneous distance between instantaneous centers. So omega 3 upon omega 4 is given as I14 upon I13 into I34 upon I34. That is the distance between I14 to I34, I13 to I34. And that concept is Arnold Arnold Kennedy theorem. So what this theorem states is, suppose if you consider three rigid bodies which have got a plane motions, their instantaneous center lie on a straight line. So what is meant by this theorem? So if you consider these three bodies, link 1 which is fixed, link 2 which is a irregular shaped body, and link 3 which is also an irregular shaped body. So obviously these three links will be having three pairs. If you use the equation which we already learned, n into n minus 1 upon 2, here there are three pairs. So 3 into 3 minus 1 upon 2 gives 6 by 2, that is 3. So this three rigid bodies have got three instantaneous center, and as you can see, link 2 and 1 are hinged together, so that hinge itself is a first instantaneous center, which I have written it as I12. I12 is instantaneous center for link 1 and 2, and similarly for link 3 and 1, I13, which is hinge for link 1 and 3, that is I13. So now I23, I have just assumed that I23 is lying at a point which is denoted as A here. So point A is the point which belongs to link 2 also and link 3 also. So this is point I A where I23 is lying. That's what I have assumed, but it might not be true also. So if it is true, if this is I23, point A should have uh, velocity which when you measure with respect to link 1 or 2, irrespective of the link with respect to which you are measuring, it should show same magnitude and direction. But here in this case it is not true. If you measure the velocity of point A with respect to link 3, that will be a velocity which is tangential to line I13 and A, which is shown as VA3. Similarly, if you measure the velocity of point A with respect to link 2, that will be a velocity which is perpendicular to line I12 and I23. And if you see, both VA2 and VA3 are not same. They are different in direction and they may be different in magnitude also. So because of this, I cannot consider I23 as a instantaneous center, because I23 gives me different values of velocity and different direction of velocity uh, when I consider this point when it belongs to different types of different links which are involved. So this will be only true when this I23 lies on a line connecting I12 and I13. So if I23 is a point somewhere on this line, then only this will be true. That means if you draw a line perpendicular to this one, it will be direction for I direction of velocity for I23. So for that reason, I23 must lie on the straight line connecting I12 and I13. Hence, Arnold's Kennedy theorem is proved. So let us take a problem. So here I have shown a crank slotted lever mechanism. If you remember, this crank slotted lever mechanism is nothing but a quick return motion mechanism. And in this problem, this crank slotted lever mechanism is used for a shaper machine, and the length of each and every link which are involved here is mentioned. So you can see the length of various links have been given, and at the given instant the angle of inclination of this link, the crank OP is also given, which is 30 degree, and the angular velocity of the crank is also given, which is 20 radians per second. So what has been asked is for link 4 and link 5, link 4 and link 5, you need to determine angular velocities, and for link 6, which is slider actually, or the cutting tool itself, for that you have to calculate the sliding velocity. So that is the problem statement. So to begin with, we have to draw a configuration diagram, and for that you need to select an appropriate scale. So here if you see the mechanism, the link length, the maximum link length which you find is 16 centimeters. So if you go for 1:1 scale, you require a larger space, and that's why I have reduced the scale to half. I am going to consider 1 centimeter as uh, 2 centimeter link length. So based on that, I have drawn a configuration diagram. So in earlier problems, many times I have shown how to draw a configuration diagram. So you need to draw the configuration diagram for this also in similar way. So here what you have to do is draw a horizontal reference line, select any one arbitrary point O, and at that point draw a line perpendicular to this horizontal line, and the length of this line should be 4 centimeter. Sorry, 5 centimeter. Why 5 centimeter? The length of link OS is 10 centimeter, and when you reduce to your scale, it becomes 5 centimeter. Similarly, draw a crank OP, for which you have to use divider and you have to set it to 120 degree. So why 120 degree? This theta is 30 degree and this is a perpendicular angle. So 90 plus 30 will become 130 degree or 120 degree. So that's why you have to mark a line of 120 degree inclination, and on that line you make mark a length of 2 centimeter. Again, why 2 centimeter? OP is 4 centimeter. So to reduce scale, you have to mark a line of length 2 centimeter. Now through this point S and this P, you have to draw a line of length QS. The length of this QS should be uh, in configuration in the actual diagram. The length of QS is 16 centimeter. So you draw it to 8 centimeter line and use divider. Place it on Q. Draw an arc of length. If you see, the length of QR is 14 centimeters, so draw an arc of length 7 centimeter. Join these two and complete the configuration diagram. So that's how you have to draw a configuration diagram. Now, next thing is I need to locate the instantaneous centers in this particular mechanism. So if you count the total number of links which are involved here, there are 6 links. Link 1, link 2, the slider is link 3, and this rod is link 4, link 5, and the slider again is link 6. So total there are 6 number of links. And as I already know, the total number of instantaneous centers can be calculated as n into n minus 1 by 2, where n is number of links involved. So based on that, I will get for this particular mechanism there are 15 number of instantaneous centers. And it doesn't mean that I need to find out all these 15 instantaneous centers. Uh, you have to find out only those instantaneous centers which are relevant for solving the given problem. And some of the instantaneous center you can directly identify in this configuration diagram. For example, all the hinges are instantaneous centers. So there are 5 hinges here. 1, 2, 3, 4, 5. So all these turning pairs are instantaneous center. For example, if you consider link 1 and 4, they are joined at this point S, and hence this is link I14. Similarly, 2 and 1 are joined by this hinge. This is I12. Slider and link 2 are joined by this hinge. So that's why it is I32. 4 and 5 are joined by this hinge I45. Slider 6 and 5 link 5 are joined by this hinge, so I56. So I have located all the hinges as instantaneous centers. Now for sliding pair, we also know that the instantaneous center lies at an infinite distance uh, perpendicular to the line of action of the slider. So I have shown those instantaneous center also. If you consider this slider which is moving on link 4, the instantaneous center of this slider lies at an infinite distance on a line perpendicular to this link, and that instantaneous center is I34. Why I34? 3 is the slider, 4 is the link on which the slider is moving. And similarly, this one for this one also I16 is located. Why I16 means 6 is the slider, I1 always represents fixed link. Please remember, all fixed links, even horizontal surface, are going to be represented by link, the common link 1. So I got some of the instantaneous centers. So for my reference, I am going to do this particular activity now. So what I am going to do is I am going to draw a rough circle. On that I am going to show 6 points, and these 6 points represent 6 links. So this point represents link 1, this point represents link 2, this point represents link 3, this point is link 4, this point link 5, and link 6. Now I am going to join these points by lines such that it will indicate each instantaneous center which has been already located here. For example, I14 is there, I am going to join 1.1 and 4. I12 is there, I am going to join 0.1 and 2. I32 is there, I am going to join 3 and 2. Uh, 3 4 is also known to me. I'm going to join 3 4. 4 5 is also known to me. I'm going to join point 4 and 5. And 5 6 is also known to me. I'm going to join 5 and 6. And I 1 6 is also known to me. I'm going to join I 1 and 6. So I have joined those points in this circle for which I already identified the instantaneous centers. Now next, let us see the problem statement. In the problem statement, what has been asked is you need to find out the angular velocity of this link 4. So that's what has been asked. So for that, the given data is the angular velocity of link 2 is given. So if you consider the ratio of omega 4 upon omega 2, it can be expressed like this. This we already studied. The angular velocity ratios can be expressed as the distance between instantaneous centers. So how this equation is written means omega link 4 and 2 are considered, so I24 is common to both of them, and for link 4 I14 I have to write link 1 is fixed 4 because in numerator omega 4 I am going to consider, and similarly in numerator here I have to write I12 because 1 is fixed link, omega 2 is there, so that's why I have to mention 2, so I12. That implies omega 4 is equal to I12 I24, the distance between I12 and I24 divided by the distance between I14 and I24 multiplied by omega 2, which is already given. So if you see the instantaneous centers here, I12 is there, which has been already located. I know I12. I14 is there, which is also located. But I24, which is common for both numerator and denominator, I don't have located it because there is no any line joining 2 and 4. So the first thing is I need to locate I24. So that's why I have shown it by dotted line. A dotted line means I need to locate that instantaneous center at. So this I24 I am going to locate based on Arnold Kennedy principle. So if you see this I24, this is the instantaneous center which is common for both the pair of instantaneous center I12 and I14 and I34 and I23. So according to Arnold's Kennedy theorem, this I24 should lie on a line connecting I12 and I14, and also it should lie on a line connecting I23 and I34, and hence this will be the point which is connecting, or which is the point of intersection between these two lines. So first draw a line connecting I12 and I14. So I12 is here, I14 is here. So this is the line connecting I12 and I14, and I34 and I23. I34 is here and I32 is here. So this is the line connecting I34 and I32. And I24 will lie on a line which is a point of intersection between these two lines, this line and this line. So I will extend this line little further. I will get the point of intersection. So this point of intersection is the instantaneous center I24. So that's what I have marked. So this point of intersection is I24. Now I have marked I24, so you can easily measure the distance between I12 and I24. So this distance you can measure, I14 and I24. This distance also you can measure, but once you measure them, again you have to convert them into actual scale. That means you have to multiply these two by 2 centimeter because you have taken a reduced scale. So do that and calculate the value of omega 4, and it comes as 5.1 radians per second. So that is the first thing which has been asked. Next, omega 5 is asked. And to find out the omega 5, I have two angular velocity ratios. I know omega 2 also, and I already calculated omega 4 also. So I have to select any one among these two, and omega 4 will be more appropriate because if you see link 5 is connected to 4 and I know omega 4, so this will reduce my work for in calculating omega 5. So that's why I will take the ratio of omega 5 and omega 4, and as we have found that omega 4 is equal to this much time omega 2. In similar way, I can write omega 5 as the ratio of instantaneous center multiplied by omega 4. So I14, I24, the distance between these two divided by I15, I24 multiplied by omega 4. So this equation I have written in a similar fashion how I have written omega 4 and omega 2. So now I need to find out omega 5, for which I need to know I14, I24, I15. All these instantaneous centers should be located. But I already know I14, it has been located. I24 is also calculated. We have already located I24 also. And I15 is the thing which I have to find out. This instantaneous center I15 has not been calculated yet. So that's why I have to calculate I15. So I15 is common to 165 and 541. That means if you draw a line connecting I16 and I65, and if you draw a line connecting I14 and I45, the point of intersection between these two lines will be I15. So first draw a line connecting I16 and I65. So I16 is here, I56 is here. So this line itself is the line connecting both the instantaneous centers, and I45 and I14. So I45 is here and I56 is I45 is sorry I45 and I14. So I45 is here and I14 is here. So draw a line connecting these two, and the point of intersection between this line and this line, that is this point, will be I15. So that's how I have located I15. Now measure the distance between I14 and I24, I14 and I24, and distance between I15 and I24, I15 and I24. So measure the distance between these two points and convert it to actual square. That means you have to multiply it by 2 again. So when you do that, you will get omega 5 as 1.7 radians per second. So that is the second answer which has been asked here. Now the third question is, you need to find out the velocity of this slider. Now if you consider this point, this is a point on slider also and the point on link 5 also. So based on this, I know the angular velocity of link 5, so I can calculate the tangential velocity at this point. So the tangential velocity or the sliding velocity of r is given as the length of this link I56 and the length of this distance I15 and I56 multiplied by omega 15. That means omega 5 itself. So omega 5 itself is omega 15. So measure the distance between I56 and I15 and calculate the sliding velocity, and it comes as 70 centimeter per second. So that's how we need to calculate the tangential velocity of slider. So this instantaneous center method compared to relative velocity method is very simple to solve, but the problem with this instantaneous center method is you can find out the velocity values only. You cannot calculate acceleration, or you cannot plot velocity acceleration polygon. So let us take some practice problem. So here is the problem statement. It is a 4-bar mechanism. I have already given answer also for this one. This is the first practice problem. So solve this and find out the answer, or just check whether the answer is matching or not. This one, which is of slider crank mechanism. So answer is also given for you. So try this and find out the whether you are getting the same answer or not. This will end up with this session. Thank you. Again, if you have any questions, please mail us at the following mentioned email IDs. Thank you once again.